It has been a very, very long time. So in order for us to re-engage and move forward into the interesting conversation we're going to have today, guys, we need to come back to this idea. If you have your notes from the previous day, maybe you want to go there. But understand this is going to be our jumping off point into what we're doing next. But guys, let's talk about the conversation that got us to this, which then leads into what we're talking about next. So if you remember, and this was 9 days ago. Wow, 9 days ago. Guys, we introduced this idea of waves. And we talked about this idea that waves have representative frequencies and wavelengths. And Bailey got us thinking again about interconverting between those. And we looked at some of that math. But then, guys, when we said that when those waves are light waves, electromagnetic waves, we can then figure out their energies. And we talked about the idea that these energies are equal to Planck's constant times the frequency of these waves. And then we talked about this idea that Planck and others then started to study the energy that was being released by these sources of light. And guys, what he found out was that light cannot transfer energy in an infinite number of amounts of energy. We talked about the idea that light is not like a hose spewing water, that as light transfers energy, it's not just this continuous stream of energy in an unlimited number of amounts of energy, but instead it's more like, I actually shot you, didn't I? Yeah. With the dart gun? Yeah. So, can I do it again? No, let's don't. But guys, we talked about the idea that energy coming out of lights is actually better thought of like a bullet. We call those bullets photons. And these photons are transferring energy in packets. And guys, not all photons have the same energy. Yellow photons, red photons, blue photons, so they have different amounts of energy related like this. But when energy is transferred through light, it is always in a multiple of that amount of energy. So if we know, remember we talked about the yellow vapor light? And we said if we can calculate the amount of energy radiated in one photon, then the amount of energy that we can absorb from that light is always a multiple of whatever that energy per photon is. And then the more photons we absorb, the more energy we get. Yes?
So that equation, does it give us a single one, or does it give us the multiple?
It gives us the energy of one photon. And this is where things get weird, because now we've got to rethink the way we think about light. So up until now, we said that light is a wave, right? Is light a wave? Absolutely. But then the thing that's interesting is light is also a particle. Now, don't think that this wave is actually a particle moving like a wave. That's not the case. So light can be perfectly described as a wave, and all of this works. But the thing that's weird is that energy that is associated with a frequency is contained in a packet that we call a photon that is literally a particle of light. It's a bullet of light. And so when we treat light like a photon, it behaves like a bullet. Just a second. When we treat light like a wave, it behaves like a wave, and we can bring those ideas together to understand energy. So we can describe the amount of energy in light as a wave that has a frequency that we can then convert to energy. But that energy is then the energy of one photon of light with that color frequency and wavelength. Is that okay? So if you know the energy of that color, all you can do, and I won't shoot you, but you're like, ugh, all you can do is absorb energy as a multiple of that number. So one photon, one dose of energy. Two photons, twice that dose of energy, but it's always a multiple of that number because it's literally being transferred as packets that we call photons. Leah, go ahead.
So what kind of energy, exactly,
Mm-hmm.
what kind of energy is light? When it hits us, does it turn into heat? Do we just like take it in like it's a kinetic energy?
It depends. So it's kinetic. It's energy that's moving, right? So it's definitely kinetic energy. More specifically, and we're not going to get into this a lot, we call it radiant energy. So there are multiple ways to transfer energy. There's conduction, me touching you. There's convection, waves moving through the air, convection ovens. They have fans that move energy through the air. There's also radiation, and this is radiant energy, but that is a form of kinetic energy. Now, what that does when it gets there is dependent on what it's hitting. So if it's energy that's hitting your black jacket, it's going to get hot. That energy is going to be converted into heat. If it's energy that's hitting a solar cell, then an electron is going to get excited and it's going to turn into current, kind of like problem 31. And so what that energy does depends on what it's hitting. Is that okay? Guys, other things that you want to talk about relative to this idea of light being both a wave and a packet and transferring energy? Go ahead.
So wait, how exactly did Planck find out the constant number for...
I don't know. And to be honest with you, it's not something we need to dig into in order to understand the concept. It's a fascinating question, Tucker, but I have no idea. Okay, so guys, if you're comfortable with what we've just said, let's then talk about this idea of quantized energy. So this is what Planck discovered. He discovered that when atoms release light, release energy in the form of light, it turns out that the energy that is coming out of these lights does not contain all the possible energies from 0 to whatever. It is not all the different energy values that are possible. Instead, when light is released, there are energies that are released and there are energies that we don't see being released. And we give that a name. We call that quantized energy. And at first it was really weird because Planck and Bohr and others are looking at this and they're going, wait, when I look at atoms that are excited, flame test lab, releasing energy, we are not seeing all the colors, all the possible energies. We're seeing some energies that are being released and some energies that are not being released. Now, guys, maybe to you that seems obvious, but in 1915, that was a really big idea. And the idea is this: if we don't see all the possible energies being released, what does that tell us about electrons? If we don't see all the possible energies being released, what does that tell us about electrons? Say it again. There are only certain places they can be. Now, guys, understand that if the plum pudding model was correct, if those electrons could be anywhere in the pudding, they can move from and to anywhere. And when we collect the energy being released by these atoms, we would see all the colors of the rainbow. But guys, it turns out that that's not what we see. We see some colors that are present and some colors that are not present. And guys, now I know it might seem a little obvious, but back then it was radical, because just like Bailey said, what that means, and this is what Bohr figured out, is there are some places electrons can be and some places those electrons cannot be. And as a result, he figured out that the electrons are organized into orbits, and that's where we get the planetary model of the atom. Does that make sense? Okay, so now guys, what we're going to do is we're going to focus in on this energy that is being released in the form of light. So putting this away, guys, this is the idea, and this is where maybe you want to start taking notes. Guys, in order to have this conversation about energy being released in the form of light, we need to talk about some terms. Spectra, which is the plural for spectrum, but the idea is this. Guys, there are three different types of spectra. There are continuous, there are emission, and there are absorption spectra. Now guys, let me just tell you right up front, the only one of these you need to know for this class is the middle one, emission spectra. But guys, let's talk about what this means. So focusing first on continuous spectra. How should I do this? I'm going to go, I think red will show up. So guys, white light. Are we comfortable with the idea that white light is actually not a thing? What is white light? All the colors mixed together. Sunlight is an example, although it does lean towards the yellow, so the yellow bands are brighter. But in full spectrum sunlight are all the colors of the rainbow. And so if you take this and if you pass this full spectrum white light through a prism, it bends. And as it bends, it separates out into all the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet, and you end up with what is called a continuous spectrum, meaning all the colors of the rainbow are present. Is that okay? Yeah?
Would it still be continuous if, like, let's say from like red to green was continuous, but then it just stopped? Would that be continuous?
So it's an interesting question. Yes, but. So we can talk about it for a second. So you understand that we're switching right now from incandescent to LED lights, right? LED light bulbs are way more efficient, so on and so forth. And if you've ever gone into Home Depot recently, when you walk into Home Depot, the very first thing you see is all the light bulb choices, right? They're there because they make a lot of money off of selling light bulbs. But if you've ever actually looked in the light bulb section, you may have noticed that there are places where they have examples of these light bulbs up above, and you can push a button and you can turn the light on. And if you've ever looked on the side of a light bulb box, you may have noticed that it has like a temperature. It says this is a cold bulb, this is a warm bulb, and really what that's talking about is the portion of the spectrum that we see in that bulb. So if you have one of these LED lights and it's towards the colder end of the spectrum, literally what you're getting is this end of the spectrum. So we still consider that to be full spectrum light, but it's more shifted towards the blue. And those are the LED lights that when you turn them on, it's like, wow! They feel really bright and almost overwhelming. But then if you get into these, they call them warmer light. And if you move towards the warmer light, the part of the spectrum that you're seeing is that end of the spectrum, more towards the yellows and the reds. We still consider that to be full spectrum. You're just missing that end of the spectrum from it. So does that make sense? Okay, all right. So guys, you good on continuous light? Okay, so now what we need to do is talk about the stuff that we need to really be thinking about, which are emission spectra. So here's the idea. Think about it this way. If electrons could be anywhere in an atom, when we flame test that atom, guys, this is what we could see. If the ramp were the model, these electrons could be falling from anywhere to anywhere, and you would get continuous light out of every atom that you excite because those electrons could be moving from or to anywhere. Well, that's not what Bohr and Planck and others found. He found this, that if you take a sample of an element, kind of like what we're going to do in lab, but instead of heating it, you pass current through it. If you add energy to atoms in a gas, those electrons excite, but they can't stay in their excited state, and they fall, and when they fall, they release that energy as light. And then guys, if we take that energy and split it out through a prism, what we end up with are bands of light energy interspersed with bands that we don't see. Now guys, here's the interesting question. Let me see if I can clean that up a little bit. Guys, what do each one of those bands represent? An electron falling. Each one of those bands represents a falling electron. Now guys, do this with me. How far did this electron fall? Not very far, right? Because it's a short fall, low energy. These electrons in this region fell longer distances. And then guys, out here, those electrons went through longer falls because they are giving off higher energy, more blue and violet light. But each one of those bands represents a fall. Does that make sense? Is that okay? Now, guys, contrast that with this. This is actually what is called an absorption spectra. And here's how it goes. Just watch, and I think this will make sense. So we excited a gas. The electrons jump up. When they fall, they create an emission spectra. Now, guys, imagine that you could take that same gas and cool it down. So now these electrons are not excited. Then you pass white light through that cold gas. And guess what that white light's going to do? It absorbs energy. The light from this white light enters into this cold gas and it excites electrons inside that gas. When you then take that light and pass it through a spectrum, the white light gives you a continuous spectrum, but do you notice what's missing? The same bands. But Jason, can you interpret it for us? What's going on here?
The white light is the continuous spectrum of the gases blocking.
Not blocking, but absorbing, and that's the idea. Here we have an excited electron falling. Here we have the same electron being excited. So the same amount of energy that it releases when it falls, it absorbs when it's excited. Do you see that? So these represent falling. These represent exactly the same electrons being excited through the same distances, and therefore they absorb the same amount of energy they then release when they fall back down. So absorption spectra are mirror images of the emission spectra because they're taking in rather than radiating energy. Does that make sense? So guys, again, you don't need to know about absorption. It's interesting, and when you get further into your studies, you will see this in college. But for now, just understand that they exist. But guys, this is the one you need to understand, and you've got to understand that these bands represent falling electrons. Is that okay? Okay, so now guys, this is the jumping off point. Bohr and Planck and others saw these emission spectra. He saw that they weren't continuous spectra. He determined that energy was quantized, and he said, oh, as Bailey said, that means there are places where electrons can be, and there are places where electrons can't be, and it made him realize that the electrons are organized into these structures that we think of as orbits. Do you get the idea? The question then becomes this: how did he make that jump towards structure? And guys, this is the idea. If you want to scratch this into your notes, you can. Guys, it goes like this: making this jump now towards structure. Structure is determined by these spectra. And guys, well, do this. This slide is all about a review of what we just talked about. So you decide if you want to write this down. I think the next slide is more important. So guys, this is the idea, and you should be able to just agree with this. So we understand that light is composed of many wavelengths. We can separate these to form a spectrum. We've got continuous absorption and emission. The one that we care about is emission spectra. They're created when energy, in this case, like we're going to do in lab, is run through these samples, and these electrons excite. When they fall, they release light. Is that okay? This then is the connection. So guys, the bands in these emission spectra then correspond to the energies that are being released as these electrons fall and transition from excited states back down to ground states. Now guys, the idea is that these spectra can then tell us about structure. But in order to figure out structure, what we need to do is we've got to figure out how much energy is associated with these energy levels. And guys, thankfully, this can be done with a very simple equation. So if this seems muddled, let me give you a second to write it down, and then I'll show you what we're talking about, and then we're going to do the magical math. You guys all caught up? So guys, if these sentences don't make sense, let me show you what we're talking about. Don't write this down. So here's the nucleus, and here's the energy levels. And say that we have an electron that falls down here, and it releases light, and that light has an energy of a ridiculously big number, 10 joules. Okay, just logically think about this with me. So guys, when this electron goes from here to here, the energy that it releases has an energy of 10 joules. Here's the question. What do we now know about, let's call this 1, 2, and 3. What do we now know about the energy of energy level 3 compared to the energy of energy level 1? It's 10 joules higher. Let's say that again. If an electron falls from 3 to 1, and if that electron releases 10 joules of energy, then we know that energy level 3 has got 10 joules more energy than energy level 1. Does that make sense? Okay, so guys, in order then for us to connect energy of light, color, frequency, wavelength, in order for us to connect that to the electron structure of atoms, what we've got to be able to do is figure out the energies of these energy levels. Thankfully, the equation to do this is really simple. You ready to do it? It goes like this. Guys, I would encourage you to draw this with me. Clean sheet. Up in the upper left-hand corner, give yourself about this much space on your paper. Guys, in the upper left-hand corner of whatever space you're going to use, guys, this is the equation. This is the equation that allows us to figure out the energy of the energy levels. Now let's define what these things are. Actually, you know what? I'm going to have you draw the picture first. This will be better. I wonder if this will work. I'll bet it will. Let's have you draw the picture. So guys, it goes like this. Draw yourself this. Oops. Sorry. I forgot my screen was frozen. So guys, draw yourself this. I think it'll be better to draw the picture first. Draw yourself a schematic of an atom. Nucleus in the middle, energy levels 1 through 5.
Wait, and it's a separate from the equation?
Well, so what we're going to do then is we're going to put the equation there.
Oh, okay.
Yeah. So guys, the thought then becomes this. In order for us to figure out the energies that are released when these electrons fall, we've got to be able to figure out the energies of the energy levels. Now to do this, we can use this simple equation. But to do that, we need to figure out what the variables are. So guys, what is N? Do you remember from last year? It's called the principal quantum number. It is the energy of the energy level. You may remember on our periodic tables, just to help you make the connection, the values go 1 to 7. These are the energy levels. But then, guys, to figure out the energy of an energy level, we need the value for RH. This is what is called the Rydberg constant. And guys, the value for the Rydberg constant is an amazingly round number. It's 100 joules. I know, right?
And always?
Yeah, it's a constant.
Okay.
Well, ooh, it's a constant in hydrogen.
How do you spell that?
Rydberg? Don't know. We'll figure it out later.
So is it?
So guys, here's what we're going to do. We're going to take this value and we are going to apply it to the different energy levels. So guys, do this with me. Energy level 1. But you'll notice that in the equation, it's negative. So the Rydberg constant is 100, but there's a negative sign in the equation. So guys, the idea then becomes this. Plug in 1 for N and solve that for energy. What's the answer? Negative 100. And if you're not sure what we're saying, so guys, what we're doing is we're taking this equation, plug in the Rydberg constant, and then divide it by 1, but it's 1 squared. Okay, so you're plugging in 1 for n, solve this, and the answer is negative 100. Now guys, do it for energy level 2. Looking at energy level 2, the numerator is still negative 100, but what's the denominator now? 2 squared, which is 4. Do the math. Negative 25 joules. Now guys, do this for energy level 3. Plugging in 3 for n, 100 divided by 9 is functionally 11. We'll call it close enough. Now guys, plug in 4. And do you guys understand the math we're doing? Okay, so plug in 4 for this. 100 divided by 4 squared, which is 16. It's functionally 6. It's close enough. And then guys, we get out to 5. 5 squared is 25. 100 divided by 25 is 4, negative 4. So guys, these values then tell us the energy for the energy levels. So we now know the energy for each of these energy levels, but now watch what that allows us to do. So guys, imagine, and you can write this in with me if you'd like. Guys, let's start in energy level, let's make this easy. Start in energy level 3 and go down to energy level 1. So if you have an electron that starts in energy level 3, and if that electron falls down to energy level 1, guys, the question is, how much energy is going to come out with that electron? Well, what is the difference between these two energy levels? 89 joules, right? So how much energy will come out in that electron? 89 joules. Now guys, what if we have an electron that goes from energy level 5 down to energy level 1? How much energy is going to come out there? 96 joules. Guys, that's the whole idea. If we can assign energies to these energy levels, then by knowing the energy of the higher energy level and the energy of the lower energy level, we can then subtract, and that difference will be the amount of energy lost when this light is released as a photon when the electron falls. Go ahead. Now this is where, you asked that question about, is R sub H always 100? And the answer is for hydrogen, yes. But other atoms have different Rydberg constants, but you only need to know it for hydrogen. Go ahead. Now it's time to have the interesting conversation. Guys, what on earth does this mean? Oh, I gotta fix this. What does this mean that this number is negative? I really don't know how to make this better. Guys, I'm sorry, I got to click through all of this again. So guys, what does it mean that this number is negative? So guys, let's talk about it. What do these numbers represent in the first place? The energies of the electrons in these orbits. And guys, understand Bailey's question is very important for you to understand. What does it mean that these are negative? So let's build into the idea. So guys, what do these numbers represent? The energies of the electrons in these orbits. So guys, if you're an electron zipping around right here, that electron has negative 100 joules of energy. If you're an electron zipping around right here, that electron has negative 25 joules of energy. If you're zipping around right here, that guy has negative 11 joules of energy. Does that make sense? So now let's talk about what that means. First of all, this. Guys, why do these electrons have energy in the first place? And Tucker, you and I talked about this before break. Why do these electrons have energy at all? Say it again. Potential energy. But guys, do you remember what we said at the very beginning of the energy unit? In order for there to be potential energy, what does there have to be? Gravitational potential energy requires a force of attraction, right? Guys, in order to have potential energy, you have got to have attraction. So this is the idea. Why does that electron have negative 100 joules of energy? It's attracted to the nucleus. Why does this have 25? attracted to the nucleus. Guys, it's all about the attraction to the nucleus, which now brings up an interesting question. What on earth does it mean to have negative energy? It's not repulsion. How can you have negative energy? And guys, the answer is it's directional. The negative is directional. And if that doesn't make sense, imagine this. Imagine that you're sitting on the surface of the earth and you dig a hole. So now, guys, you've got a hole like this. Get the idea? So this is elevation 0. This is elevation minus 1 foot, 2 foot, 3 foot, 4 foot. So now it makes sense to have negative distances, right? Because it's a negative distance against a 0 point that you're below. So now, guys, what about this? If this is negative 5 feet, how much do you have to jump to get out of the pit? 5 feet. If this is negative 100 joules, how much energy do you have to add to get out of the pit? 100 joules. And that's the idea. In just a moment. This is the amount of energy that you have to add in order to get that electron out of the atom. Is that starting to sound like PES a little bit? That's the idea. This is the amount of energy that you've got to add to get that electron out of the atom. So you got to add 100 joules to this dude to get it away, 25 joules to this one, and so on. But now, guys, this brings up an interesting idea. We said that if the electron falls from here to here, guys, which one has more energy? Energy level 3 or energy level 1? Which has more energy, 3 or 1? 3. Because if you fall from 3 to 1, you release energy. And if you're releasing energy, that means 3 has more energy than 1, right? Okay, now here's the idea. How do we see that in the numbers? Well, guys, which number's bigger, negative 11 or negative 100? Negative 11. So, guys, the idea is we see that this energy level has more energy because it's less negative. Now, if that's the case, what is the maximum energy for an energy of an electron? 0. So think about it. Negative 100, negative 25, negative 11, negative 6, negative 4. These numbers are becoming less and less negative. And as we were to put in 6 and 7 and 8 and 9 and 10 for the energy level numbers, those numbers get smaller and smaller and smaller up to a maximum of 0. Does that make sense? But guys, what does that 0 mean? And that 0 means 0 attraction for the nucleus. Huh? See how that comes all the way around? So guys, imagine that we put in a ridiculously big number here. Like imagine we put in energy level 50. So if we put in energy level 50 there, 50 squared is 2,500, and 100 divided by 2,500 is a very, very small number. It'd still be negative, but it would be all the way, it would be a very, very small negative number. But what if we put in infinity for n? Then it would be 0. But it's an asymptote, right? Because we never technically get there. But the idea, guys, is as we move out from the nucleus, we're moving through bigger and bigger energy levels, and the energy gets smaller and smaller and smaller as a negative fraction up to an asymptote of 0, which is the point where that electron is no longer attracted to the atom, and that means it's gone and the atom is ionized. Do you see how all that fits together? Questions about this idea of negative energies, Rydberg constant, this equation, all of that good stuff. Do you understand the fundamentals of it? Okay. So now, guys, we've got to let the cat out of the bag. The Rydberg constant is not 100. The Rydberg constant, you were. The Rydberg constant is not 100. Guys, the Rydberg constant is actually 2.18 times 10 to the negative 18th. Yeah. But guys, here's the thing. If I had told you 2.18 times 10 to the negative 18th, you would have got so bunged up on that number that you never would have been able to divide that number by 4 and 9 and 10 and 16 and so on. So it's much easier for me to teach you the principles using an easy number like 100 and then throw you the actual value now. And now you still understand the concepts. It's just the math is a little harder. Could you tell though I stumbled on it a little bit? I was like, it's not round, it's pretty. I didn't know terse, I just threw it out there. And then guys, n is the principal and then somebody, was it Leah, said, how do you spell Rydberg?
Yeah.
It was we'll get there. But guys, the principle still holds. And this is where this becomes really, really interesting. Because guys, now we can start answering very, very practical questions like this. This is how we're going to end the day. So guys, imagine that we have, and if you want to write it down, you can, an electron that starts. And again, we should come back to Alice's point because this is important. Guys, we're only going to do this for hydrogen atoms. The math is more complicated for more complex atoms because of the shielding. So we're only going to think about this for hydrogen. So guys, imagine that we have a hydrogen atom, and imagine that we excite that electron to energy level 4. And then that electron falls back down to energy level 2. Here's the question that we're going to figure out. What color is the light? What? Yeah, and that's the trick, right? Guys, how do you figure this out? Now, guys, let's talk about the problem-solving process, and then we'll actually get the answer. So if you're reaching for a calculator, you're way ahead of yourself. So guys, remember the question is, what color is the light? So if that's the question, how do we get there? Well, what's the first thing that we need to know about the light that is released? We need to know its energy. So guys, in order to know the energy of the photon, what do we need to know? The energy of energy level 4 and the energy of energy level 2. What will we then do with those numbers? Subtract them. And by subtracting those, we will then know the energy of the light. Then, once we know the energy, we will take that energy and we will convert it into frequency. Then, once we know the frequency, we will convert that into wavelength, and then we can go look at the picture and figure out the color. We could do it with the frequency as well, but I want to go to wavelength because that's the better blowout that we have in that diagram, and frankly, because that's what they're going to have you do on the test. But you're right, we could do that straight to frequency if we had the right picture. So guys, you understand the process? Then let's do it. Here we go. So guys, in order to do this, I'm going to redo my drawing. So we've got bump, 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 4 to 2. So guys, the first thing that we need to know is the energy of energy level 4 and the energy of energy level 2. So let's do this. Everybody on the lake side of the room, figure out the energy of 2. No, you guys do 4. Everybody on the mountain side of the room, do energy level 2. And I'm on the mountain side. Those are mountains, that's lake. I'll do mountainside. So guys, mountainside is energy level 2. So energy is equal to negative R sub h divided by n squared. Negative R sub h is not 100. Negative 2.18 times 10 to the negative 18th joules divided by 2 squared, which is 4. So 2.18 times 10 to the negative 18th. Okay, mountainsiders, did you all get negative 5.45 times 10 to the negative 19th? Hey! All right, Lakesiders, what did you guys get? Sarah, did you say 1.36 times 10 to the negative 19th? Okay, Lakesiders, can you confirm or refute? Good. Okay. So guys, with that said, let's call timeout and let's think. Does this make sense? Is that number bigger than this number? Yes, because it's less negative. Good? Okay. Now guys, when you get this wrong on the unit test, here's why. I'm about to show you where you're going to screw this up. Subtracting these numbers makes people's heads go, pow. This is how to do it. Go back to the equation. Guys, change is always final minus initial, right? So change in energy is equal to energy final minus energy initial. Or energy, guys, where did we finally end up? 2 or 4? 2. Minus the energy of 4. Slow down and do this, and it will keep you from screwing up. Now, guys, the energy of energy level 2 is negative 5.45 times 10 to the negative 19th minus a negative 1.36 times 10 to the negative 19th. Now, guys, before you touch your calculator, should the sign be positive or negative for the answer? Negative. Why? What does that tell you? The energy is being released. So we've got negative 5.4, let me just do it again. Negative 5.45 times 10 to the negative 19th plus 1.36 times 10 to the negative 19th. And guys, I get negative, thank goodness, 4.09 times 10 to the negative 19th joules. Okay. So here's what we know. What does the negative tell us? The energy is being released. Just like endo and exothermic, our system is always the atom. And if that number is negative, it means the energy is being radiated in the form of a photon. You guys good to there? Okay. Now let's take this energy and let's convert it to frequency. So we know that energy is equal to this. Negative 4.09 times 10 to the negative 19th joules is equal to, I don't know Planck's constant. 6.63 times what? 34. And that's joule seconds times x. So we've got negative 4.09 times 10 to the 19th, 6.63 times 10 to the negative 34th. Divide that. And I may have some rounding errors, but I get negative 6.17 times 10 to the 14th hertz. Now, guys, let's talk. At this point, we now know the frequency of this light. What does the negative mean? It's radiated, but guys, at this point, I like to drop the negative. Because we've already established that the light is being radiated, the negative is no longer necessary. You can't have negative hertz. So I drop the negative at this point because that is the frequency of the energy. And then, guys, Bailey, you're absolutely right. We could stop there, and we could probably associate that with the color. But let's take the last step, and let's associate it with wavelength, because that'll be more easily done. So 2.9, is it 998? 2.998 times 10 to the 8th meters per second is equal to x times 6.17 times 10 to the 14th hertz. So we have 2.998 times 10 to the 8th divided by 6.17 times 10 to the, oh, not negative 14th, 10 to the 14th. And guys, I get 4.86 times 10 to the negative 7th meters. What's that? That's the next thing I wanted to talk about, Robbie. Guys, be really careful here. A not small number of people, it was like 4 or 5 years ago, people went bananas on this one. There was a question just like this on the AP test, and the question didn't ask for color. It asked for what is the wavelength of light that is emitted from this fall from 4 to 2 in nanometers. And guys, a crazy number of students got to this point and got the question wrong because they didn't convert to nanometers. It was really frustrating. But Robbie, you're absolutely right. This is 486 nanometers. Oh, I should put units on that. Okay. So then, guys, to bring this full circle and have sort of that experience, so 486 nanometers. 486 nanometers works its way backwards to somewhere in here maybe. Yeah. It's pretty high energy.
So when you get your answer that's gonna spit out, so it's 4.6 times 10 to the negative 7, do you need to do like dimensional analysis, or can you just write it in?
No, you can just convert. Yeah, unit conversions like that are just the process of pushing decimals. You don't need to represent. Yeah, just a sec.
So I was getting into my book to look at the chart thing,
Yeah.
and I was having to turn to the page, and they have the Rydberg constant with different numbers of units. Very different. It's not on the AP equation.
Oh yeah, this is one of them that they took off the test. So, what page are you on? Oh yeah, no. So the problem here is that they're actually solving. They're solving for wavelength. Yeah, it's a different iteration of the constant. No, the value, but it should be here. So look with me on page 215. Do you see it there? In equation 6.7. Oh wait, at the very top.
Oh, yeah.
There it is. So what are they calling that? They're, where R sub h are Planck's. And they're bringing them all together.
They have the Rydberg constant. It's like the Rydberg constant times Planck's constant and the speed of light.
Yeah, so that's the value that we're using. Okay. So guys, thoughts or concerns? Let me ask. Oh wait, Caleb. Yeah.
I was just wondering how you
Oh, so this is going to be your thing. I love it. So the idea is this, that when we were here, in the same way, let's go the other direction. Imagine if you were given 486 nanometers and you wanted to go to meters. We would go 486 times 10 to the negative 9th, and that would be this number in meters. But then putting it in proper scientific notation, we'd go 1, we'd go 2, and that would be 4.86 times 10 to the negative 7th, which is then this. So the idea is that if we're going from meters to nanometers, this is 10 to the negative 7th. Nanometers is 10 to the negative 9th. So going 10 to the negative 9th makes the exponents 2 steps smaller. So this number has got to get 2 steps bigger. Is that okay? Yeah, I know it's a little crazy. So guys, relative to homework then, this is what we got.
Oh, that's so weird.
No, it's really not bad. So, guys, let me